1 is on the counting principle, permutations, and combinations. Okay, so we're going to have this whole chapter is on probability, lots of probability problems. Okay, so the very first thing is the chart that you guys had on your activities. So you don't have to fill it in now. I just went ahead and filled it in right here on my notes. So you can see it. You can fill it in later if you want. So it says much of probability has to do with counting the number of ways that certain events can occur. So for instance, suppose you want to know the probability of rolling a 7 with a pair of dice. Then you could fill in this handy table to help you count the number of possibilities. We know that there's a total of 36 outcomes. 6 outcomes for the first dice, 6 outcomes for the second dice, and when you multiply them, you get a total of 36. So in other words, 6-1 is different than 1-6, and that's why I gave you guys 2 different colors of dice when you guys did that activity, so you can tell that they're different outcomes. Okay, so if I want to find the probability of rolling a 7, then I could have a 1-6, a 2-5, a 3-4, a 4-3, a 5-2, and a 6-1. So there would be a total of 6 ways of rolling a 7, and the probability would be 6 out of 36, which is 1-6. So if I ask something like, what is the probability of rolling less than 5? Well, less than 5 would mean that I would roll a 4, a 3, or a 2. So I would have all of these outcomes here. So there would be a total of 6 out of, again, the 36. So we would end up with 1/6 again. And I could ask lots of different questions. So I could say, what's the probability of rolling an even number? What's the probability of rolling where at least one of your dice has 2? You know, I could ask lots of different things, okay, about this chart. Okay, but in the previous example, it was possible to list all of the possibilities. We could do this handy little chart with 36 outcomes, and we could see all the different possibilities, but sometimes it's nearly impossible to write everything out. Okay, when you have things like 1,000 choices, you don't want to list all the possible outcomes. It would take forever. So in order to do that, we use what we call the fundamental counting principle. And when you look at it in this little box, it's very confusing. So it says, let E1 and E2 be 2 events. The first event, E1, can occur in M1 different ways. After E1 has occurred, E2 can occur in M2 different ways. Then the number of ways that the 2 events can occur together is M1 times M2. And like I said, it's kind of confusing when you see it all with variables. So let me give you an example. Okay, so here's the example. What if I'm doing that thing I talked about earlier where I roll a die? So I have possibilities 1 through 6, and then I flip a coin. So I have heads or tails. Okay, I had 6 possibilities for the first one, and I had 2 for the second one, so I end up with a total of 12 possibilities. Okay, does that make sense? So what you're doing is you're really just doing a tree diagram, which we just discussed. A tree diagram shows you the total number of possibilities. Okay, so this first one, it says Cold Stone Creamery has 10 different choices of ice cream, 12 different choices of toppings, and 3 different sizes of waffle bowls. Okay, if Edward wants to get a waffle bowl, 1 kind of ice cream, and 1 topping, how many different ways can he choose this dessert? We don't want to draw a tree diagram every single time. This is what Emily was saying, like, isn't there an easy way? There is an easier way. Okay, if you don't have to draw the tree, then we don't do it. Sometimes you don't need a tree. Sometimes you really do need the tree. In this case, we don't. So we say, well, the first thing I'm going to choose is a waffle bowl. And in order to choose the waffle bowl, I know that there are 3 different sizes. Okay, and after you choose the waffle bowl, you want to pick what kind of ice cream. So he's just going to select one of the ice creams out of the total of 10. So we have 10 choices. And then once he selects the ice cream, he's going to pick 1 topping. So there's 12 different choices. So you have 3 times 10 times 12. If you did the crazy tree diagram, you would have 360 different branches. Okay, that would take forever. Okay, but these obviously get harder. So we're going to have some where he's not just choosing 1 topping, but he's going to choose like 3 toppings, which, I mean, if you're going to Cold Stone Creamery, aren't you going to choose more than 1 topping? Come on now. Yeah. So we'll do some harder ones later on. All right, so number 2, it says a true-false quiz has 5 questions. How many different sets of answers are possible? Okay, what are you guys thinking? That's what everybody always thinks. They always think it's 10. It's not 10. What is it? It's what? Not 25. Okay, let's think about it. The first question, right? I could have true or false. So I have 2 possibilities. The second question, I could also have true or false. I have 2 possibilities. So right now I'm at 2 questions. I could have true, true. I could have true, false. I could have false, true, or I could have false, false. There's 4 different things. But now if I add a third question, I get even more. I could have all of those things with a true on the end, or I could have all of those things with a false on the end. So I have 8. This is the 4th question, and the 5th question. So we get 2 to the 5, which is 32 possibilities. So if I asked you what's the probability of getting a perfect score if you go in to take a quiz that you know absolutely nothing about. So if I went in and I tried to take a quiz on Russian, I know no Russian. I should not be taking a quiz on Russian. And if I totally guessed and it was true false, I would have a probability of 1 out of 32, around 3% of getting a perfect score. Not going to happen, right? Okay, so next one. So a multiple choice quiz has 7 questions, each with 4 answer choices, A, B, C, or D. How many different sets of answers are possible? So we have 7 questions now. 1, 2, 3, 4, 5, 6, 7. And each of these choices could be A through D. All right, so how many choices do I have for each question? I have 4. So 4 choices for the first one, 4 for the second. So 4 for all of them. So when I multiply all of these together, I end up getting 4 to the 7. Okay, and if I find 4 to the 7, I get 16,384. That's the number of ways to answer a 7-question multiple choice test with answers A through C. Crazy, huh? A lot of different possibilities for an answer key. All right, so let's do a combination of those. Let's say we have some true-false questions, some multiple choice questions. So it says an exam has 10 multiple choice questions with choices A through D and 5 true-false questions. How many different sets of answers are possible? Okay, so now I have 10 multiple choice questions. As much as I want to draw out 10 little blanks, are we past that point? Can you guys kind of do it without that? So if I have A through D, I have 4 choices. So I'm going to have 4 choices 10 times. It's like 4 times 4 times 4, 10 times, right? And then the true-false questions, I have 2 choices for each of those, and I have 5 of those questions, so 2 to the 5th. So I find 4 to the 10th times 2 to the 5th. Okay. I get 3355, 4432. So 3,554,432. Okay, number 5. So in 2007, a Marion County license plate began with the numbers 49 and then had a letter followed by 4 other numbers. Okay, so this is kind of a random thing. Like license plates back when I was growing up, when I was 16 and first learning how to drive. Like I was from Delaware County, so the numbers that we had were 1 and 8 on our license plate. So we had 1 and 8 at the beginning of our license plate, and then the last, so then it was a letter and then 4 numbers. So everyone from Delaware County had a 1 and an 8. Okay, that's how it was. So Allen County was Fort Wayne. They were always a 2. So you could tell where people were from based on their license plate. So this was always exciting when you were on the highway and you saw someone with a 1-8 on their license plate, because you'd be like, oh, maybe it's one of my friends. And you'd like totally creep out the people and stare at them as you drove by. And they probably, like, often it wasn't anybody that you knew. Okay, so anyway, so this is how license plates used to be. And then they are no longer like that. So Marion County used to have a 4 and a 9 at the beginning. So I'm just going to go ahead and put those in a box. So that's not like 4 choices, 9 choices. That's just, it's already, those numbers are already there, 4 and 9. And then we have a letter, and then we have 4 numbers, 0 through 9. So in Marion County, the total number that we could have was 26 letters, and then 0 through 9, how many numbers are on that list? 10, right? 1 through 9 would be 9, and then the 0, so 10, 10, 10, and 10. So when I multiply these together, I get 260,000. So the question is, do you think that this is an adequate number of plates? And it could be yes or it could be no. I don't know. What do you guys think? So it says the approximate population of Indianapolis was 782,000. Would it be enough? Why? It's not enough people, right? But some people argue that it is enough. And I agree, it could be enough. Why could it be enough? Not everyone has a car. You could have a family of 1 car, or you could live downtown and not need a car at all, just walk to work, right? So some people don't have cars, and then the population also counts people who can't drive, right?
What about people with cars who can't drive?
Yeah, and sometimes people have a car, like have multiple cars. So then it's like, well, this person has 6 different cars sitting in their garage. So they need a license plate for each of those. So I don't know, it's debatable. But in Indianapolis in 2007, that's when we stopped the license plate thing. I call it the license plate game. You can always tell where someone's from. But it stopped because Marion County actually, they had 49, and then they started using 99, 98, and they went backwards. Because we don't have 99 counties in Indiana, right? So they used up all of the other ones. But then Allen County, Fort Wayne, got too big. And then that's when they just kind of got rid of with the license plate thing. All right, so the next one says an ID code consists of 2 of the digits 1 through 5, followed by 3 letters A through D. So maybe this is some kind of code that you put in as you go into your job or something like this. Maybe something you wear on your badge. I don't know. So an ID code, 2 of the digits 1 through 5, 3 letters A through D. And you're allowed to repeat numbers or letters. So you can have 22ABC and you can have 12AAB. Okay, so I have 5 choices for the first one, 5 choices for the second one, right, 5 numbers. And then I have letters, A through D. So I have 4, 4, and 4. So I multiply. So I have 20 times 4, so 400 times 4, 1,600. So 1,600 total. Guys, stop.
Yeah.
Okay, but some people are not very smart about their codes for anything. When I was in 8th grade, my password for getting into my email was password. And I wondered why someone hacked my account and sent out spam mail to all of my friends. Why did they do that? How did they know my password? Because my password was password. Like, I'm stupid. Who does that? But I thought it was very clever as an 8th grader. Oh, I'll just make a password, right? But some people are very stupid about their bank numbers too, like their little codes or their garage codes. Like making it your birthday probably isn't a good idea because people can access that information. They can go on your Facebook and find your birthday, right? Not very smart. So making like your bank code your birthday is not a good idea. Other things that people make their bank codes, 1111. That's a terrible decision. That's the first thing that someone will try when they're trying to steal your bank card. They will try 1111 and then 2222. Yes?
Maybe people think that people that are trying to steal their identity won't think it because it's too stupid.
No, everybody tries that. And when people can program computers to hack into things, those are the first things they try, right? So banks have gotten smarter since when bank cards first came out, and they have now, most banks don't let you repeat. So some might have like a couple repeated numbers, but for the most part, they try not to make it like 1111, 2222. Does that make sense? They'll give you a random code and it's not repeated. So let's say we have this one. So it says repeat example 6, but now make the additional stipulation that we cannot repeat numbers or letters. So if you can't repeat numbers and you can't repeat letters, then that means I have 5 choices for the first number. But once I select one of those numbers, let's say the number 2, it's out. I can't have it for the next one. So how many choices am I down to? 4. Okay, and then let's say I choose A through D. So I have 4 choices for A through D. But then once I choose that first one, like B, then I can't have B. So I have A, C, and D. So I have 3, and then 2. Does that make sense? How that works? So I have 5 times 4 times 4 times 3 times 2. Is that 480? Will you check that for me? Okay, I think it's 480. Okay, but there could be lots of different things. So this next one says, well, what if you cannot repeat the letters, but you can repeat the numbers? So I can't repeat the letters, so I'm going to have my 4, my 3, and my 2, but then what am I going to have out front? 5 times 5, right? And I think that makes 600 if you multiply it out. Okay, so does that make sense? That's called the fundamental counting principle. That's a very important thing in probability. All right, and I often will call it the slot method. Do you guys see why I call it the slot method? Like you fill out little slots and you're just putting in the numbers. I like the slot method. I think it's very easy. Okay, now permutations, you can always use the slots. So if you prefer the slot method, which I actually do for permutations, I just use the slot method instead. Okay, so these are going to be 2 different things, permutations and combinations. I'm going to describe the difference. Okay, I have 8 nieces and nephews, but 4 of them are from one family, and their names are Eleni, Bridget, CJ, and Devin. They make the perfect probability problem, A, B, C, D. So we're going to talk about A, B, C, and D. So let's say I'm selecting 3 of them. So let's say I select Eleni, Bridget, and Devin. Okay, and I want to have some kind of competition. And I want to see who's going to get first place, second place, third place. Okay? Eleni, Bridget, Devin is different than Bridget, Devin, Eleni, or Devin, Eleni, Bridget, right? Does that make sense? These are all different. how many possibilities would I have if I rearrange these? If I start with, I would think about what we just did, the slot method. How many choices for the first one? 3, and then I have 2, and then I have 1, right? Does that make sense? Okay. Now let's say I didn't know who I was choosing though. CJ was still in the mix. Then when I do my blanks, I would have 4 choices for the first one, 3 choices, and then 2 choices. If I was only selecting 3 of them, but they were in a certain order. Okay, that's going to be a permutation. So permutation is where something like order matters. So I want you to think about 3 words. So the first word is going to be positions. The next one is going to be places. And the last one is going to be president. So when this is going to matter is when we have things like ribbons, like places, right? The order matters when you're passing out ribbons. Like Yaya would not like to get the 10th place ribbon if he actually got first place in the shot put. Agreed? You want to get that first place ribbon. You don't want to get 10th place. So it matters. Okay, but combinations, it will not matter. Combinations are going to be things like clubs, committees, anything where there's just a group of people. So it's a group of items. Okay, so permutations is places, positions, presidents, and so on. Okay, combinations are committees or clubs. And the way that you find these items is if I have R item or N items and I select R of them. So like what I was saying, I had four nieces and nephews. I was selecting 3 of them. So N was 4, R was 3. I do this by doing N factorial over N minus R factorial. Okay, and I'll explain where that formula comes from in just a second. You might also see this as NPR on your calculator. Yeah, National Public Radio. Yeah, NPR. All right, combinations. Combinations you're going to see as C, N, comma, R. And it's going to be almost the same thing, but you're going to have one more thing you divide by. So it's going to be N factorial over N minus R factorial, and then R factorial. So you have an extra R factorial on the bottom. Okay, so that's going to be like if I have my 3 nieces and nephews that I selected, but Eleni, Bridget, and Devin are the same as Bridget, Devin, Eleni. Like these would be the same thing, right? All those different groups would be the same. Does that make sense? Because I'm just selecting them for some kind of club or committee. They're just all going together. If I said, okay, we're all going to get in the car, we're going to go out to dinner, right? It doesn't matter what order they get into the car, right? It doesn't matter who is first, second, and third. We're all going together. So it says in permutations, the order matters. Permutations can be found with the slot method we used before. So there's a little explanation of this down here, so it would be good to read. But it's basically saying like what I just said. If I have ABD, that's the same as DBA in a combination. But they're different for permutations. Okay, so order matters for the permutation. So let's try some problems. So the very first one, so it says, how many ways can I arrange the letters A, B, C, D, E, and F? Okay, I have 6 letters. If I'm rearranging them, then I can think of the slot method. I have 6 choices for the first one, and then I have 5, 4, 3, 2, and 1. Okay, that makes a total of 720 ways. This could be solved using the slot method, which I just did, or permutations. If I had done a permutation, then I would do P, 6, 6. I have 6 items. I'm putting them in 6 slots. Okay, so with the formula, it was 6 factorial over 6 minus 6 factorial. It was N factorial over N minus R factorial. So what happens is you get 6 factorial over 0 factorial, which is 6 factorial over 1, which gives you the same thing as 720. Do you see how the slots are easier? Like, I don't want to go through all that work when I can see right away that it's 720. The slots are a little bit easier. So B says, well, what if I only have 3 of the letters and I'm trying to arrange them? Okay, that means that I have 6 letters, but I have only 3 slots for them. So I go 6, 5, and 4. Okay, 6 times 5 times 4 is 120. So how does this work? In my formula, that means I have 6p3, right? I have permutation with 6 for my n and r is 3. So I have 6 factorial over 6 minus 3 factorial. Stop rolling the die. So I'm going to have 6 factorial over 3 factorial. Think about this. How is this related to what we just did? Can someone tell me how that's related? Yeah, Alex.
It's because the 6 factorial is 6 times 5 1.
Mhm.
You would just be like 6 times 5 times 4.
Exactly. That 3, 2, 1 is gone. That's why I didn't have the 3, 2, 1 there. I divided it out. Does that make sense? That's where the permutation formula comes from. It comes from this law method. Do you guys understand what he was saying? The 3, 2, 1 ends up being divided out. It doesn't matter. So it's gone. Okay, so C. So how many ways can I create a group of 3 letters? So the group means that it doesn't matter what order I have. So like C, B, A is the same as A, B, C. Okay, that's a combination. Because it's a group. The order doesn't matter. So that's when I'm going to do C, and then I'm going to have 6 letters, and I'm going to select 3. Okay. This one we're going to do with the formula, and then I'll talk about why this formula is true. So I'm going to do 6 factorial over, I still have my 6 minus 3 factorial, but we also have a 3 factorial out front. So I have my 6 factorial over 3 factorial, 3 factorial. So I always say the shortcut is just to write like what you would have had with a permutation, 6, 5, 4, but then you divide by that second, the 3 factorial. So you do 3, 2, 1 on the bottom. So the bottom you're dividing by 6, yeah. So see how you get the top, 6, 5, 4 was 120, divided by 6. Well, the 6 and the 3 and the 2 reduce, so you get 20 in the end. Okay, let's think back to my Eleni, Bridget, and CJ. Why am I dividing by 6 in particular if I had Eleni, Bridget, and CJ? We're talking about groups of people. How many ways can I arrange? Yeah. I can arrange them 6 different ways. I could do Eleni, Bridget, CJ, Eleni, CJ, Devin, or Eleni, CJ, Bridget. You know what I'm talking about? So I can arrange those 3 people 6 ways. This has divided out by the number of repeats. That's what I was doing there. I'm dividing out the number of times I repeated them. All right, so next up. So 6 5th grade students are competing in the spelling bee. How many different ways can they place? That's my key word, permutation. Permutations can always be used with slots. So I have 6 students. So I have 6, 5, 4, 3, 2, 1. 720. All right, the next one. Allison was given 8 choices in her art class for an assignment. She is to choose 3 of them to be due on Friday. How many different ways can this be accomplished? What do you think? Combination or permutation? Combination. Why? Yeah, they're all due on the same day. It's a group, right? It's a group of assignments all due on the same day. So we do C, 8, 3. Okay, you should be able to do this without your calculator. We'll be talking about this a lot more, but if I have C, 8, 3, here's what I do. Whatever my second number is, 3, that's the number of slots I have on the top. So I'm going to do 8, 7, 6. And then on the bottom, I'm going to divide by my 3 factorial. Because how many ways can I arrange 3 things? 6 ways, right? 3, 2, 1. And then I can reduce it out. So see how the 3 and the 2 and the 6 reduce out? So right away I get 56 without even touching a calculator. 56. It's also one of the numbers in Pascal's triangle. We've talked about that before. Yeah, so you might also see, instead of 8, choose 3. Remember, you might also see like that. We've talked about that before with Pascal's triangle. Same thing. All right, next up. So 15 students are interested in an upcoming community service event, but Mr. Morrison only has room for 6 more students. So how many different ways can he choose these students? What do you think? Combination, permutation? Combination. Order doesn't matter, right? Combination. It's just a group of students. They all have the same duty. So at most schools, if you think about it, most schools, when they do their student council, don't they do like the president of the senior class, the vice president of the senior class? They do all that. What do we do? What do we call it? Stewardship. Doesn't matter who, we don't have a president, a vice president, do we? So most schools will do a permutation when they do president, vice president, secretary. We do combinations. Does that make sense? Okay, so anyway, so this is 15, and we're choosing 6. This is one you probably don't want to do without a calculator. It would be kind of messy. So you can use your calculator. Remember, you want to first hit 15. Then you want to hit the button that says math and arrow over to PRB for probability. You're going to go down to option number 3, which is NCR, and then you're going to hit 6. So when you do that, you get 5,005. All right, number 5, there are 12 countries competing for the Olympics in team gymnastics. How many ways can you get gold, silver, and bronze? Permutation combination? Does it matter if you get gold, silver, or bronze? Yeah, it matters. So this is a permutation. So you're saying 12P3. 12 countries select or put the 3 in slots. So 12 countries, 3 slots. So really, that's when I just do the slot method. I say 12 times 11 times 10. That's all I'm doing. So I get 1320. Okay, does that make sense? You could also do the formula, which is 12 factorial over 9 factorial. So the 9, 8, 7, 6, 5, those all go away. You could do that as well. All right, next up. So this is where it gets a little bit harder. Is everybody with me? I know it's a long lesson. You got to pay attention now. All right, so again, Cold Stone Creamery has 10 different choices of ice cream, 12 different choices of toppings, and 3 different sizes of waffle balls. When we go to Cold Stone Creamery, we don't just get like 1 ice cream and 1 topping. Like, let's be real. Like, I get a lot of toppings. Okay, and if I'm getting 2 different types of ice cream, really, if I do chocolate and then vanilla, which I never would do, boring. If I do chocolate and vanilla, isn't that the same as vanilla and then chocolate? I say the same thing. It doesn't, because actually Cold Stone, you mix them together anyway, right? You put it on the flat and mix it all together. So they are the same thing. So we're not worried about what's on the top of the cone and so on. You guys understand what I'm saying? So when I first started teaching this, I made a mistake. I always admit when I make mistakes. And I did. I made a mistake. I said, okay, we're going to choose the ice cream. Don't write this down. And then we're going to choose 2 types of, or no, wait, we're going to choose the type of waffle bowl, and then 2 ice creams, and then we're going to choose 2 toppings. And I said, okay, there's 3 choices for waffle bowls. There are 10 choices of ice cream, but I can't choose the second one, so I'm going to do 10 times 9. And then I said, okay, and the toppings is going to be 12 times 11. And that's how I taught my students. And then I realized, oh, wait, this isn't right. Because I just double counted everything. So I double counted when people got chocolate and strawberry and chocolate. I put an order to it when there shouldn't have been. So here's what we need to do for these types of problems. So we need to say, we're going to pick the waffle bowl. And then we're going to pick the 2 ice creams. And then we're going to pick the 2 toppings. And it's actually a combination problem within a slot problem. There's 2 different things going on. Because for the waffle bowl, yes, I agree, I still have 3 choices. But for the 2 ice creams, what I have is 10 choose 2. 10 choose 2 is 10 times 2, or 10 times 9 over 2 times 1. It ends up being 45. Okay, but what I had previously was 10 times 9. I had 90. Do you see why that's wrong? Because, like I said, chocolate strawberry is different than strawberry, or it's the same as strawberry chocolate. I've double counted. I counted all of those as different things. They aren't. They're the same. So the 2 toppings, I have 12 toppings. I'm going to choose 2 of them. Now you can get all technical and be like, oh, but you have to put the syrup on before you put the sprinkles. We're not going to do that. It's all together. They're going to mix it together anyway, right? All right, so I have 3 times that. So I have 3 times 45 times, what is that, 66? 12 choose 2, 66. And I get 8,910. That's a 10. That's the number of possibilities. It's a lot, right? So the same kind of thing happens with this. So Jenny is going on a trip. So Jenny, you're going to California. You decide it's going to be warm. You only need 1 pair of pants, just in case, 4 shirts, and 3 pairs of shorts. So how many ways can she do this? Okay, so it's the same idea. You want to talk about the number of pants she has, the number of shirts, and the number of shorts. Because it doesn't matter if she takes her blue shirt and then her red shirt and then her purple shirt and puts them in that order. It's still the same suitcase as if she had done the red, the blue, and then the purple. Do you see what I'm saying? It's the same. You're just saying she has a certain number of shirts, you're going to select a few of them. Okay, so for the pants, she has 8 pairs of pants. She's only selecting one of them, so it's like 8, choose 1. It's the same as 8. You could have just written 8 there, like I did here. Like that was 3, which is 3, choose 1. All right, and then shirts. She has 10 to select from, and she's choosing a group of them. She's choosing 4 shirts. And then the shorts, there's 7 pairs of shorts, and she's selecting 3 of them. So 8, choose 1 is 8. If I do 10, choose 4, I get 210. And if I do 7, choose 3, I get 35. So we multiply all those together. And that's my answer. So 257,250 possibilities. So when you say you have nothing to wear, let's be real. Maybe it doesn't go together, but whatever. All right, next up. So it says there are 7 girls and 6 boys and invisible children. I know that's no longer existing. We'll say Global Citizens Club. So from this group, a committee of 4 will be chosen to go to Uganda. How many different ways can a committee be formed that contains at least 3 girls? So if I'm going to have at least 3 girls and I have 4 people total, I'm either going to have 3 girls or I'm going to have 4 girls. I can't have 5, 6, 7 because I'm only picking 4, right? So I'm going to say, how many ways can I have 3 girls go and 1 boy? And then how can I pick 4 girls? Okay, so let's start with the 3 girls and 1 boy. I have a total of 7 girls. I'm selecting 3 of them. Each of those 3 girls could go with each of the 1 boys you choose. So I'm going to multiply by 6, choose 1. Okay, does that make sense? So if I have Natalie and Livy and Emily, all 3 of them could go with any boy on the list. They could go with Yaya, or they could go with Garrett, right? So that creates another possibility. So that's why you multiply those. Because then you can have the other 3 girls. Other 3 girls can go with, like you have different sets. Whoa! Does that just make you very dizzy? Thought I was erasing. Okay. Anyway. So next up, so what about the 4 girls? That means that we have 7 girls that we're choosing from, and we choose 4 of them. You could also do 6, choose 0 for the boys. It ends up being 1. So when I do that first one, 7, choose 3, 35, times 6, I get 210. And when I do 7, choose 4, I actually get 35. 7, choose 3 is the same as 7, choose 4 because of Pascal's triangle. Remember, it's very symmetric. Choosing 3 people to go is the same as saying choosing 4 people to not go. They're the same number. All right, so what do you think I do with these last 2 numbers, 210 and 35? There's 210 ways to pick 3 girls and 1 boy. There's 35 ways to pick 4 girls. So how many total do I have? You add them, yeah. So you get 245. And a lot of people think you multiply, but it's not like that group is going with the other group. Like every combination of those 2. Does that make sense? It's either this one or it's that one. All right, and then these last couple are pretty easy. So how many ways can you rearrange the letters in the word picture? This is just like if I had the letters A, B, C, D, E, F like we did before. You're just rearranging them. So I have, in this case, 6 letters. So if I'm rearranging them, it's just 6 factorial.
7.
Oh, 7. Pretend I can count. I heard Kelsey first. Kelsey gets bonus point. 7 letters, so 7 factorial. So 50, 40. So there's 5,040 ways to rearrange these letters. But then it gets a little bit tricky, because what if I have bookkeeper? And what do you notice about bookkeeper that's different than, there's lots of double letters, there's lots of repeat letters in particular. So how many letters do I have in this word? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, I wanted to know 10. I have 10 letters total. But what happens is, let's say I started out with OO, and then I did K, E, P, I don't know, lots of different stuff. I could have had my OO like that, or I could have switched them. And that creates a different outcome. But it's really the same outcome. So it's kind of weird. I've now double counted. I've double counted all those O's. I double counted all the E's where they could be, like they could switch around a whole bunch. So think about it. If I have 3 E's, think of them as E1, E2, and E3. How many ways can you rearrange those? 6. We've talked about this a lot. 3 factorial, right? So what I'm going to do is I'm going to divide by those repeats. So I'm going to divide by 3 factorial. That gets rid of all the double counting from the E's. And I'm going to divide by 2 factorial, and I'm going to divide by another 2 factorial because I had 2 O's, 2 K's, and 3 E's. Okay, so I divide them out. So the easiest thing to do would be to do your 10 factorial, 10 math factorial, and then divide by parentheses, so put these in parentheses. Don't look for a factorial in each one. You know 3 factorial, it's 6. So 6 times 2 times 2. So you get 151200. That's your answer. So you look for the number of repeated letters, and you divide by those under a factorial. That's the pattern.
She's going to give